Hey everyone, I'm Rahul and I'll be presenting a project which is called Bandwagon, Stop Following the Crowd. Um, so one of the problems that we identified with traditional DAO voting, for example, Snapshot, is that a lot of that voting is very centralized and very out in the open. And that's the problem with most blockchain-based voting. It's completely in the public for anyone to read and anyone to manipulate as they feel fit. So our mission is to empower DAOs and communities to make critical decisions through end-to-end privacy. And the current DAO voting challenges, I already talked about centralization risk, for example, Snapshot, the bandwagon effect. So how the bandwagon effect works is, suppose I go to vote on a protocol, and I already see that there are a million stake votes for yes, and only 10 votes for no. I instinctively am biased towards voting for yes. So that's the bandwagon effect. And obviously there's lack of privacy, as in users' vote is not private, how much they've voted is not private. And all of these can lead to manipulation, coercion, etc., which are all massive problems, especially in a decentralized world. So how does Bandwagon go about solving this? So we use something called time-locked encryption and homomorphic encryption. So the idea is that partial homomorphic encryption would let us add if we encrypt a user's votes, so how much they're voting. So if I say my vote is, if we specifically talk about DAO voting, my vote is 10 tokens, I will encrypt that with a known public encryption key, and then we can do addition over these fuzzed data or these encrypted data, and no one would actually know the actual values, whether it be the individual add-ins or the sum. So time-locked encryption basically lets us encrypt something for a given period of time, and after that, trustlessly becomes public. For example, for homomorphic encryption, we would generate a key pair. The public key will be given to all the users. The private key will be given to DRAND to encrypt for the voting period, say 100 seconds. And after 100 seconds, that private key becomes public for everyone to see, so that they can decrypt the ballot, which is how much votes have been for candidate A, for candidate B, and verify the election results for themselves. So that's a very generic process for how time-locked encryption will work in this case, and how we will use homomorphic encryption for the same. Now, one of the biggest problems is we can do all of this on chain, but at what cost? A user is never incentivized to pay money to cast a vote. If you want users, in fact, all users from every strata of society, whether it be someone with $10 in their account or whether it be someone with $10 million in their account, to be able to vote. However, since we are living in a decentralized world, we want this to be done trustlessly and in a verifiable manner. So we use recursive snarks where an aggregator is able to take all user votes and keep on aggregating them together, where the final proof will prove validity of the entirety of the votes, entirety of the proofs that, or the votes that came behind it, however long that chain may be. And this way we can provide a succinct proof for the entire voting process. The only attack vector that exists here is that the aggregate might censor your votes. But because all of the votes are encrypted and anonymous, an aggregator does not have any incentive to censor any particular individual just because they don't know who they're censoring. They might be causing themselves harm by censoring someone. Cool. So one of the problems that we found was we wanted homomorphic encryption over addition. So we wanted to add over the encrypted encrypted space. No great solution existed as of today in the libraries that we were looking for, especially ElGamal. ElGamal is partially homomorphic over multiplication, but we can use exponentiations to do addition, but it's not great because to go back, you need to implement a lookup table for large values. So we started looking at traditional crypto systems, and we came across the Palier crypto system, which is additive homomorphic. Now, the Palier crypto system is hard to implement in a circuit, but that's great. A user doesn't have to actually encrypt their values inside of a circuit. They only need to give encrypted values, and we can decrypt them and verify that the encrypted value is indeed the encryption of some witness that they're providing. And addition over the Pallier crypto system is fairly easy. If you define cipher C as the encoding of M, encoding of M plus 1 is simply multiplication of those two ciphers divided by n squared, where n is the common modulo. So if you decode this encrypted value, you'll simply get M1 plus M2, and you can do this in n number of steps, and finally decode the value to get like a sum of n steps, which is what we're going to leverage for our solution. So this is the security of the implementation. I'm not going to talk about it a lot. So we were time restricted by how much we could implement. So since we were using Snarky.js for our implementation, we were limited by the kimchi field, the field prime FQ. So we have to keep all of our operations, especially the multiplication and the modulo, inside the single field element, which means the bit length of multiplication of two ciphertexts should be less than 254 bits. Which means a single bit length of a single cipher is 127, and so on. So the conjectured bit security of our protocol comes out to be about 31 bits, which is not great, easily brute forceable on maybe my phone as of today. But that's okay, because this can be easily improved by implementing a big integer arithmetic library in Kimchi, which is going to be a future improvement to this project. So what does the application workflow look like? So before the proposal, the DAO sets some election parameters, and the front end of where the user is like some user or like someone from the DAO is creating the election. They set a random proposal ID. They generate a key pair, give the private key to DRAN to encrypt for the entirety of the voting duration, and they create a base recursive proof for the aggregator to use with the encryption key as a public input so that it's visible to everyone. Sorry, encrypted version of the an encryption public key, and also the encrypted version of the private key so that it can be downloaded later. So during the voting period, every user casts their vote. So we have recursion horizontally and recursion vertically. So at every step, when a user submits a vote, they create a client-side proof of their vote, and they give it to the aggregator. The aggregator verifies the user proof and deems that it is valid, verifies the old aggregation proof, so the latest state of the aggregator, and then applies the user proof to the old aggregator state to get the new aggregator state. So this way, recursively, you can verify all computation throughout the voting process. For posterity, we can also store all individual user proofs on IPFS, but it's not needed because recursive proofs are validity proofs for the entirety of the votes that came, entirety of the proofs that came before it. So after voting, and here's the good part, DRAN automatically reveals the encrypted private key for everyone to see, and they use pairing cryptography for this. The aggregator submits the final proof on chain to Mina that acts as the final commitment. Anyone, in this case Bandwagon, and this could be a user as well, can get the encrypted ballot from the contract, can also get the encryption, like the decrypted private key, and then get the results and verify the results themselves. So in this case, a user never has to trust a centralized entity for the results. They can verify each and every result by doing a very small computation themselves. This is how the user proof circuit looks like. The public inputs are the encrypted votes, the election ID. This is what the logic flow looks like. The private inputs are the signature, where a user proves that they are indeed the holder of a certain public key, which they claim to be, because someone could simply say, okay, this public key holds 10 or 100 balance, and I want to vote with it, but they might not be the owner of it. So they have to sign the election ID with their public key, with their private key, to prove that they are the owner of the corresponding public key. This is what this aggregate proof circuits look like. Again, I won't go much into it. The public input is a user proof. Private input is a nullifier non-inclusion proof. the preceding aggregator proof. Although the user proofs can also be private, there's nothing stopping us from doing that. And we verify a couple of parameters and then update the aggregator proof. That's it. I would love to show a demo. Maybe I can. Let me see if I can. Is that visible? Cool. So the front end is fairly simple. If I want to create a proposal title, I can simply say, okay, Antalpha should have a 1-month hacker house in India. And I will give a description on how many funds we're requesting from Antalpha to do this, and what the costs are going to and what the costs are going to look. And that's going to get rejected 100%, but you could try. And then we can set the proposal deadline. So in this case, I can simply say the proposal expires on, say, the 27th at 10 a.m. at 10:05 a.m. And I will simply go publish proposal. It's not going to do anything right now because I don't have the Mina wallet installed, which I need to connect. So the connect wallet, yeah, I don't have Aura wallet yet. But yeah, it will ask me to sign the transaction. The transaction will be sent to IPFS, where every user can get it. You go to the voting page. Yeah, oh, it was able to fetch the old proposal. This is the old proposal that we published to IPFS. So some proposal with some abstract and with some random voting deadline, where a user is able to vote yes or no, depending on whether they're eligible to vote yes or no by signing the transaction. And there's actually a missing page here for voting results. And yep, that's how truly trustless voting looks like. It's called Bandwagon. Although the official name is going to be ZK Snap, because we want to be in competition with Snapshot.
Question.
Yes.
So you do only ZK over the encryption, no, membership proof.
Yes. So we verify membership proofs. Well, there's two ways to verify that a person is eligible to vote. Either you can create a Merkle tree beforehand and do membership proofs, or you can use storage proofs from any chain to prove that a user held balance X in a storage slot Y at some block Z, which was the starting the voting period.
So right now it's kind of like a semaphore. So
yeah, currently it works kind of like semaphore. We're integrating storage proofs. We're halfway through implementing ZK storage proofs in Kimchi for Ethereum, and this way a user will be able to prove their balance off-chain.
And the homomorphic part is in ZK, is not in ZK.
No, the encryption of the homomorphic encryption is not ZK, which is fine.
Right.
A user only giving the homomorphic encryption and their vote of the, so they'll give their vote and the homomorphically encrypted vote, and we decrypt the vote and check that the vote is equal to the decrypted value.
Right. And the private key is being emitted by like the time sensitive thing.
Yeah, the time lock encryption, correct. The private key is, yeah, for the homomorphic decryption, the homomorphic encryption. And the addition over these encrypted values, so addition over the homomorphic encryption is actually done by the aggregator circuit inside of ZK circuit.
Right, right. And what about like the public keys that are used for homomorphic encryption?
Yeah, the public key is available for everyone, because so how anyone can join to vote as long as they're eligible. So every user can create a proof. The aggregator can create a new proof whether or not, depending on whether or not a user's proof is valid.
How does the time thing work?
Oh, time locked encryption. So DRAND is a network run by Ethereum Foundation, Filecoin, and a lot of other good parties, which is a public goods project, and it's free. DRAND. Yeah, decentralized randomness. So every 7 second, it's a random number. So the good part about this property is you can tie those random numbers to a pairing check, so that you can say this can only be decrypted by the random number that's going to be available at block 30. This way you can time lock something, like time lock.
Related to how the random number was being generated.
Correct. Yes.
This is probably the hash chain or something like that.
Correct. It's a pairing check, but yeah.
Right. Okay. Makes sense.
Any other questions? Yes.
So, what are numbers of each vote like be revealed at the end of the vote?
Yes, the ballot will be revealed because the private key becomes available. Each individual user's vote still remains private.
I mean, like, but the thing is, like, if you have the number in the end, you can just like easily, not easily calculate, but just like calculate, find a subset of like each DAO members, because like each one has the
Right.
number of tokens.
I mean,
Easily compute.
right. It is possible, but with assuming that there are a large number of
Like,
users, this becomes the knapsack problem, but like a harder version of the knapsack problem.
Yeah.
And it's assumed to be computationally infeasible with large numbers. So
But I mean, like,
yeah, if you have like 1,000 DAO members, it might be. But here's the thing: if you have 100 coins in your wallet, it's not necessary that you're voting with all 100 coins. You might be voting with 99.5.
a subset of like entire-
No, as soon as you go 99.5, it almost becomes impossible to figure out what each individual add-ins were. So this is going to be an improvement. We're going to add a very small salt.
But that was so bad.
Yeah.
Because like because like if like in the NFC DAO,
Yep.
it won't be a problem because like each one
Exactly.
has one or two,
Exactly.
typically one or two like NFTs, but for an ERC20 token, like DAO, like each
It would
one
make much more
has a
sense.
very, very specific number of tokens. And that has like a lot of problems to this.
I agree. And we can just like add a private input from the user, which is just a very small random number, a salt, which can be added to the tokens. Yeah. And which will not have any significant value in the total votes, but it will fuzz it enough that you can't recreate individual votes. Any other questions?